So for this week, we are pleased to have Zoe Yan here, and she also said briefly actually did her undergraduate here at Stanford. So welcome back to Stanford. It's good to see you here again. And Zoe did her PhD at MIT studying strongly interacting both Fermi gases and ultracold molecules. And now she is a Dickey Fellow at Princeton and is going to talk to us about more results of molecules. Take it away.
Yeah, thank you everyone. Before I get started, I'd especially like to thank the search committee and the administrators who made my visit possible. And it's a great honor to share with you some work that we've been doing studying quantum many-body physics with ultracold molecules. So before I get started, I have to motivate why quantum many-body physics is an exciting or challenging field. I really like this quote by the late physicist Phil Anderson, who said that more is different. The ability to reduce everything to fundamental laws does not imply the ability to start from those laws and reconstruct the universe. The standard model at this point tells us very well how we can understand the dynamics of a few, let's say, electrons, but that is no way to study from first principles the phenomenology behind technologically important and challenging materials such as the cuprate superconductors, or materials with non-trivial topology, or recently the very elusive quantum spin liquid state. Luckily, Richard Feynman proposed a very general solution to this issue. He said that nature isn't classical, and if you want to make a simulation of nature, you better make it quantum mechanical. And that's what I do for a living. I build these analog, continuous quantum simulators out of ultracold atoms and latent molecules to study phenomena whose properties are intractable to classical numerical computation. And I use the toolkit of these ultracold quantum gases. So atoms and molecules you can think of in some sense as nature's perfect qubits. There's no disorder, no defects. Every atom is the same as every other atom of the identical species. And there are a lot of great tunable degrees of freedom in our quantum toolkit. Degrees of freedom such as the density, the dimensionality, internal degrees of freedom, which are much more complicated for molecules than atoms. Those internal levels exhibit very long coherence times. These particles can be motionally cooled and trapped using lasers and other potentials. And very critically for my application, you can tune their inter-particle interactions, whether it be the van der Waals type or the electric dipolar interaction. And finally, depending on your choice of species, you can study many-body problems with bosonic or fermionic lasers. So the idea behind quantum simulation is pretty simple. You simulate a complicated system with one that's maybe easier to control in some way. In our case, atoms and molecules, and you know that the physical principles directly translate between your system in the lab and the target Hamiltonian. Let me introduce what I mean by ultracold. Now, from our high school physics intuition, we know that at high temperature, particles behave kind of like billiard balls. They follow these classical pinball trajectories. But that all changes when you go down to lower temperatures. When the interparticle spacing is comparable to their de Broglie wavelength, particles must actually be thought of as waves, not balls. And at this temperature, it starts to matter whether these particles are bosons, in which case they'll condense into one macroscopic ground state, or fermions, in which case, due to Pauli blocking, they fill up all allowable energy levels up to the Fermi energy. In the lab, it is now quite routine to create these bosonic or fermionic quantum gases. Here pictured is a DEC, here pictured is a degenerate Fermi gas, where we literally trap thousands to even millions of these atoms at nanokelvin to microkelvin temperatures. If you've never seen a cold atom lab, this is what one typical type of experiment might look like. At the heart of the system lies an ultra-high vacuum chamber where our atoms live. At MIT, these were cooled down to around 100 nanokelvin, that order. But we actually use no cryogenics at all. We start with these metallic vapors that are heated in ovens up to several hundred Kelvin to generate enough flux. And then from the magic of laser cooling, including Zeeman slowing, magneto-optical trapping, evaporative cooling, we span 9 orders of magnitude in their temperature. That's bigger than the difference between room temperature and the surface of the sun. So we definitely stand on the shoulder of giants in my field because each one of these successive steps pretty much won its own Nobel Prize in the past 40 years or so. And even though the schematic is nice, this is what a typical lab looks like, a jungle of PNC cables and optics. Let's not talk about that. All right, so let me give you a flavor of what quantum simulation with multiple atoms has accomplished in the past few decades. This field got a tremendous spur about 20 years ago from the realization of a textbook quantum phase transition, the so-called superfluid to Mott insulating state, where by placing rubidium atoms on an optical lattice, which is a crystal made out of light, and tuning their interactions, people were able to realize translating from a superfluid state to a state that actually the motion was frozen out and became a Mott insulating state. Cold atoms have been also critical to probing the physics behind the famous BEC-BCS crossover, which has been a paradigm in condensed matter physics. Here pictured is a rotating fermionic superfluid where you see the spontaneous formation of a vortex lattice, because of course in a superfluid, circulation must be quantized into vortices. Recently, people have been studying lattice trap gases to study, for instance, Hubbard-type models. The Hubbard model is a minimal electronic model that's thought to capture some of the phenomenology behind the cuprate superconductors. So people have been exploring various areas of the phase diagram and taking snapshot images where you can perhaps see antiferromagnetic correlations in these systems. And very lately, there has been beautiful work done at Harvard realizing the long sought after quantum spin liquid state with highly excited Rydberg atoms placed on the links of a Kagome lattice. So I was involved in none of this research, but hopefully it gives you a sense of what is possible in our field. My very small contribution to the field of cold atom quantum simulation was realizing a so-called polaron in a mixture of bosons and fermions. A polaron is a quasi-particle first thought of by Landau, which is basically an impurity coupled to a bath. And with the magic of cold atoms, we can actually tune the interparticle interaction between the impurity and the Bose-Einstein condensate. And we observe several signatures of quantum critical behavior in that system. I'm actually here not to tell you about cold atoms, but what I consider an exciting frontier of our field, which is going to involve ultracold molecules. So first, in the outline, let me tell you a little bit about why I think molecules might bring additional utility to our quantum toolkit. Then I'll tell you in brief how we create them coherently in the absolute ground states of the system, how we can probe their coherent properties and find that they are very nice two-level systems with very long coherence time, and how we can turn on their interactions with this long-range electric dipole-dipole interaction. More recent work done at Princeton, I'd like to tell you about how we introduced a novel readout modality called quantum gas microscopy to image these cold molecule systems. Using this readout modality, we're able to take single snapshot images of very closely spaced together molecules and therefore measure their spatial and spin correlations in situ. And this all culminated in a recent work where we realized several lattice spin models of quantum magnetism using these dipolar cold molecules. So since they were first created over a decade ago at this point, ultracold molecules have become a strong frontier in AMO sciences. So for the non-experts in the audience, here's a very simplified level diagram of a diatomic molecule, energy versus internuclear separation. So like the hydrogen atom that you study in quantum mechanics, this molecule will have electronic states. It has fine structure and hyperfine structure. But unlike atoms, because of the nuclei, it also has quantized vibration and rotational sublevels. So this rich zoo is not found in a single atomic species. But this rich zoo of internal states actually give us greater controllable degrees of freedom that allow molecules to be, in some sense, richer quantum simulators for various interesting phenomena. You can also study ultracold controls chemical reactions where the initial quantum state is completely defined. Molecules have also been a frontier for precision spectroscopy for fundamental physics. For instance, the state-of-the-art measurement of the electron's electric dipole moment doesn't come from a big collider experiment, but comes from a tabletop molecule experiment. And finally, molecules have also been proposed as candidates for scalable quantum information processing. What do we gain from going from atoms to molecules? Well, we inherit all of the degrees of freedom that atoms had, but we have more. We have vibration and rotation. We have long coherence times demonstrated between many of these internal states. We can control the motion with electric fields and microwaves, and for heteronuclear molecules, we can tune their electric dipolar interaction. In the past many years, there have been two kind of complementary approaches to creating these ultracold molecules in the quantum regime. One I'll call association from already cold atomic ensembles. This was pioneered by the group of Debbie Jin and Jun Lee. Since then, many groups around the world have managed to create degenerate Fermi gases of these cold molecules by associating together two alkali species, for instance, sodium and potassium. And the advantage with this method is cooling atoms is already well known at this point, so we leverage all of that technology, and we can create record-setting low temperatures with large numbers of molecules populating single internal quantum states, and this can be used to study both spin and itinerant physics, so physics where the motion of the molecule is very important. More recently, people have started to directly laser cool molecules. This is tough because molecules do not have nice closed two-level systems that make optical cycling a little bit more challenging. Nevertheless, there have been heroic efforts culminating in recent demonstrations of single calcium fluoride molecules, for instance, trapped in these tightly focused optical tweezers. Very beautiful single-shot fluorescence results here. The advantage of this approach is that you have detection capability, control capability on the single particle level with rapid cycle times. However, these molecules are, as of yet, still quite hot at 10 microkelvin or thereabouts, and thus are only useful for studying spin physics and not yet for physics of motion. So in my work, which I'll tell you about, we primarily use the first method. However, the latest work at Princeton also leverages the single molecule detection capability. So I'll be telling you all about that. So in detail, how do we create our ultracold molecule ensemble? Well, first we prepare degenerate or near degenerate mixtures of quantum gases. At MIT, we use the bosonic sodium, which you can see has Bose condensed, forming a bimodal distribution, as well as the degenerate Fermi gas and potassium-40. From this, we actually perform a magic trick. We use what's known as a magnetic Feshbach resonance to adiabatically transform the state of two free atoms into a very weakly bound dimer. And this is because you can think of, as a function of magnetic field, there's an energy resonance between the state of two free atoms with a loosely bound molecular state. And because of hyperfine interactions, there's an avoided crossing, so you can transform a large fraction of atoms into molecules as pictured here. But these molecules are still internally very hot. We want to end up in the absolute ground state of the system, which is much more stable. So to transfer from the so-called Feshbach molecule to the absolute ground state, we perform a totally coherent two-photon optical pulse sequence called SIRA, and we can transfer the vast majority of our molecules this way. So I want to emphasize that this doesn't heat up the ensemble's motional degree of freedom. So we literally end up with thousands to tens of thousands of NAK molecules, all within one internal state at around 100 nanokelvin. So now that we're in the ground state, let's try to understand the internal level structure of the molecule. We have to understand the degrees of freedom before we can leverage them. So that is done from rotational spectroscopy. So you can understand the low-lying energy states of the molecule using this picture. You have a rotational ground state, n equals 0, and a rotationally first excited state, n equals 1. Here I've neglected to depict the hyperfine substructure, which is a much smaller energy scale. And by shining in microwaves from our originally n equals 0 molecule, we can excite to various n equals 1 substates and look at the absorption of the microwave versus its frequency. And these are gigahertz microwaves. So commercial sources are readily available. And we can see that the absorption peaks happen exactly where we predict. The color lines are no free-fitting parameters, first principle theory from this single molecule Hamiltonian. So all this is to say we understand the single molecule very well. And not only that, we can also do coherent dynamics, for instance, by driving Rabi oscillations between two specific internal states. Not only can we manipulate the rotational degree of freedom, we can also change the hyperfine spin. So, for instance, in the n=0 rotational state, there are a big zoo of hyperfine spin states that is very difficult to be driven directly. However, we can perform a 2 microwave photon Rabi pulse sequence to transfer from what I'll call the spin down state to the spin up state. And that is shown here and on Rabi oscillation. So since we're atomic physicists, almost the first thing that we want to do anytime we have a new system is to quantify the coherence time, or the T2 time, in a 2-level system. So anytime you use particles for quantum applications, whether it's simulation, computation, metrology, you really want long coherence times. Otherwise, you have unavoidable talking to the environment. So to quantify that, we perform classical Ramsey spectroscopy, where we initialize everything in the spin-down hyperfine state, perform a pi/2 pulse. So this block vector goes onto the equator of the block sphere, wait for a variable precession time, and then perform a readout pulse. So we did this naively expecting pretty short coherence times, but we saw that our Ramsey fringes actually persisted all the way down to the second scale before the contrast disappeared. So that at the time was the first and longest measurement of hyperfine coherence, or any type of coherent 2-level property between trapped ultracold molecules with a T2 star time of 700 milliseconds.
So does this Ramsey have echoes in it?
Great question. This one did not, but I'll tell you about a more recent study that we did. Right. So why should you care? Well, there has been a proposal that molecules might be interesting as qubits for quantum information processing, because you have one physical system that we demonstrated enjoys very long nuclear spin coherence times between two various hyperfine states. And that can be a very robust storage of quantum memories. However, what I haven't demonstrated yet is that molecules also talk to each other via the electric dipolar coupling. And that's much faster and can generate fast dating between various qubits. So in one physical system, you can combine both the fast gate operation but the robust quantum memory. This proposal was originated by Dave Kuno. So that's a nice transition for me to talk about leveraging the electric dipolar interactions that all heteronuclear molecules enjoy. So up until now, you could understand everything that I've said using the single molecule framework. But now we need to talk about 2 or more molecules. So as you learned from intro ENM, the dipole-dipole interaction can be written with this form. It's heavily anisotropic due to this polar angle dependency here. It's long range, falling off as 1/r³. And crucially for electric dipole molecules, it can be tunable, ranging from 0 to a finite value that's totally controlled by the experimentalist. I will also point out that there are other platforms that also leverage the dipolar interaction. So to have an electric dipolar interaction, you need a lab frame dipole moment. So you might have this idea of a molecule like H2O as having a body frame orientation, a body frame dipole moment. But this is a quantum mechanical object. So in the absence of any symmetry breaking external fields, that dipole will time average to 0 in the lab frame and be pretty much useless. So we need to engineer a lab frame dipole moment. And if you look at the dipole operator, it's just the charge times distance. It clearly couples opposite parity states. So by mixing opposite parity states, you can build up a lab frame dipole moment. Now, the most intuitive way that you can see this is just apply a static DC electric field. The molecules will orient, and that field mixes all opposite parity states, which are states of rotation in our molecule. For technical reasons, we actually prefer the following method. We can directly couple 2 opposite parity states, an even and an odd rotational state, using microwaves. So your intuitive picture should be that the rotational ground state is just an s orbital, a sphere. The rotational excited state could be a donut. And so when you couple a sphere and a donut, what you get is this time rotating dipole, this rotating peach, as I like to call it, which is coherent and in phase with the microwave drive. Now that you understand the picture of one molecule, let's talk about 2. So the dipolar interaction has to be parameterized by this collision angle, theta. So as theta equals 0, two colliding molecules will always come head to head. So that is clearly going to be a repulsive interaction. But as theta sweeps to 90 degrees, sometimes it's head to tail, sometimes it's head to head. On average, it's a head to tail attractive interaction. So it becomes a simple exercise to write down the expectation value of this rotating dipole as a function of its collision angle. And you see that it is heavily anisotropic, changing from repulsive to 0 to attractive. So let's consider what happens in the lab when we have two or more colliding molecules. For us, these molecules are fermionic, and at low energies, fermions gather with the p wave partial wave predominantly. So this is the interaction potential of two colliding molecules versus their distance. So the total incoming flux, since it's quantum mechanics, must be conserved. So that incoming flux can either be reflected into the initial channel, which we would call an elastic collision. It can be reflected into another hyperfine state, which we would image as loss, or it can tunnel through this p-wave barrier. And actually at short range, there's a mechanism where our trapping light causes a photochemistry event, a chemical reaction that also loses us photon colliders. So by measuring the amount of loss in our system while cranking up the dipolar interaction, we can actually indirectly quantify the rate of dipolar collisions in our system. So that's something we did at MIT. So I won't get into the details, but here are the results of engineering dipolar interactions with the so-called microwave dressing approach. So on the y-axis, we have the effective collision rate, or you can think of this as a loss rate that we measure. On the x-axis, we have the microwave detuning, with 0 being on resonance dressing. And perhaps not surprisingly, when we dress on resonance, we see the fastest interactions happening, and these fall off with detuning. I should point out that in the absence of any dipolar interaction, we measure a background collision rate of the blue star. So your takeaway here should be that this is a very flexible platform, because just by turning on microwaves, we can span 3 orders of magnitude or thereabouts in the dipolar collision rate. So far, going back to the outline, I've laid out a few key ingredients that hopefully establish molecules as a compelling quantum platform. We can create them all in one ground state at ultra-cold temperatures. We can manipulate those internal states that can be very coherent, and we can turn on these dipole-dipole interactions. Next, I'll tell you about more recent work done at Princeton, where we developed this new type of readout called quantum gas microscopy for molecules, where we can image with single site resolution individual molecules trapped in little potential wells called an optical lattice. That enabled us to measure spatial correlations. So I'll tell you about a Hamburg round twist type experiment we did. And our latest work, which was realizing lattice spin models, was important to study the dynamics in a quantum mechanics. So let me tell you in brief about the experiment at Princeton. So here we have kind of enhanced technology to cool and trap these polar molecules. At Princeton, we use a bosonic species, sodium rubidium. We trap it in a 2-dimensional optical lattice. So schematically, this is just the egg carton potential that you see here, where molecules will deterministically occupy the absolute ground vibrational state of each potential well. If you think of this well as a harmonic oscillator, the molecule motional wave function is in the n equals 0 state. We like sodium rubidium because it has quite a large electric dipole moment compared to the other bialkali species, and the optical lattice gives us very fine control over the molecular wave function, as I just explained. So let me tell you a little bit about quantum gas microscopy. So this is a technique used in the cold atom community since 2009, and John Simon is one of the pioneers here, where the basic gist is that you can perform site-resolved imaging of single atoms trapped in some 2D periodic potential. So this is actually a hard problem, because the optical lattice constant is on order an optical wave, because they're made out of lasers that interfere. So we basically have to perfect our imaging system almost down to the diffraction limit in order to be able to resolve two particles that are so closely spaced. But we need the close spacing because we want the molecules or atoms to talk to each other. But it turns out you can do this if you build a high enough numerical aperture microscope objective and both simultaneously laser cool and fluoresce these particles. You can collect enough fluorescent photons to resolve images such as this. And this has been a big game changer in the field of cold atoms, allowing, for instance, snapshot images of antiferromagnetic ordering. Here you see atoms in one of two spin states form a checkerboard, almost kind of like an AL state classically, when people were using this to study Fermi-Hubbard type Hamiltonians. So this has been done for many atomic species, and now we bring this technology on whole molecules as well. So let me briefly tell you about the experiment. The theorists can go to sleep for 2 slides. So we formed molecules in the typical way now. We start off with individual magneto-optical traps of rubidium and sodium, and then using a combination of laser cooling, optical molasses, evaporative cooling, we end up with dual Bose-Einstein condensate. Next, we need to squeeze that into 2 dimensions. So we apply a light sheet potential, a couple of other lattice potentials, and then we crank up this 2-dimensional optical lattice, this egg carton, by interfering a laser beam. And then we perform the Feshbach association again by sweeping the magnetic field. And our atoms, whenever we have a latticite that has a single rubidium and a single sodium, that adiabatically converts with almost 100% efficiency into the state of the Feshbach molecule. How do we do the microscopy? Well, we can't image the Feshbach molecules directly, so what we do is we break it apart into 2 free atoms, again, using a microwave photon, and then we get rid of one of the atomic species with an optical pulse, and then we laser cool, just do optical molasses really, on the remaining rubidium, and collect those fluorescent photons in our microscope. This produces high contrast, single shot images, such as the picture on the left, and we can use easy digital reconstruction to basically digitize the positions as pictured on the right. Now, this microscope allows us to look at in situ local filling fractions. For instance, our rubidium gas alone can achieve almost 80% filling of the lattice at the center of the cloud, and it falls off as a function of radial distance from the center. Our sodium rubidium, unfortunately, right now, is at most about 17 to 20% filled. And we think this is due to some technical imperfection in preparing the sodium spin state, which we cannot image in our microscope. But we are working on technical upgrades to bump up that sodium rubidium filling, hopefully to near unity. But now that we have this microscope, we can now actually probe local correlations between individual molecules. So the first experiment that we wanted to explore was a Hanbury-Brown twist type experiment, where we would expect to see bunching of identical bosons. So for those of you outside the quantum optics community, let me first introduce what the HBTFS is. So this was a landmark experiment done over a half-century ago by astronomers, actually, where they had a chaotic source of light from a mercury lamp. It was split into 2 by a beam splitter, and the photons impinged on one of 2 PMTs, so these 2 detectors. Now, these 2 detectors could be translated relative to each other, so to be equidistant or at different positions compared to the mercury source. And to their surprise, Hanbury, Brown, and Twist found that once the detectors were equidistant from the source, they found more than expected number of basically intensity correlations that were higher than they expected. And in our modern language, they measured a positive or a G2 function, which is a normalized intensity distribution function that's greater than 1, which is the boring uncorrelated value. Now, modern quantum optics tells us that the G2 function can at most be this value of 2 for completely identical bosons. So there's a nice quantum mechanical interpretation of this effect. Let's say you have your particles, doesn't matter photons or bosonic molecules, originating from 2 lattice-sites A and B. And at time 0, you suddenly turn off the lattice and let them freely evolve. And after some time of flight, you collect them on 2 spatially separated detectors, 1 and 2. Now, these are identical bosons, so you don't know whether they took the black path or the blue path. and quantum mechanically, those must constructively interfere. So if you write down the G2 function as a function of this detector separation, you'll expect to see a sinusoidal variation in the G2 function. That's if you have 2 particles. What if you have more? Well, if you have 6 particles, the G2 correlation fringe becomes narrower and more peaked, and it can be mathematically shown that the peak width is inversely related to the in situ cloud size. So we exactly do this with our gas of cold molecules. We have a stochastically sparsely populated initial sample, which at time 0, we turn off the lattice and allow for 2D expansion into the plane. And at some later time, we ramp up the lattice very quickly, so imaging the momentum space, and take snapshots of these much more dilute samples of molecules. So here are our results. We first benchmarked this technique with our cold rubidium, just because it's easier and we have a greater signal to noise there. And this is the G2 function versus both X and Y displacement reconstructed from our microscope images, and the G2 function is just defined here. It's just the density-density correlator. And you can see clear interference features popping up. And if you take a one-dimensional cut through the data, you'll find almost the quantum limited value of a G2 function of 2 at a position that we expect. Now we repeat this experiment with molecules. So our sample is more dilute, so the interference fringes are much harder to see, maybe invisible in the back. But if you take a one-dimensional cut through the data, you'll find that we have a positive G2 signal with pretty high contrast rising above the error noise floor of the system. So the takeaway here, if you learn nothing else, you should understand that the microscope was totally crucial for us to detect these spatial correlations between a very dilute ensemble of non-interacting molecules. But the title of my talk was quantum many-body physics, and the HBT effect can pretty much be understood in like a single particle picture. There's no interactions between those Feshbach molecules. So to understand and create correlated states of matter, we need to actually turn on the dipolar interaction between various ground state molecules. There have been very nice theory proposals, one picture here, that suggest polar molecules in 2 rotational states could be a very rich toolbox to study various lattice spin models of quantum magnetism. So these are textbook models that, for instance, can help you understand transport in magnets. And to do that, we need to transfer the Feshbach state into the ground state with the exact same 2-photon procedure that I mentioned before. And I acknowledge that the group of Dajun Wang at Chinese University of Hong Kong was the first to produce sodium rubidium in its absolute ground state. So for us, the pathway was well known. We did this transfer. And again, we take advantage of microwaves and directly couple 2 opposite parity rotational states in order to turn on the dipolar interaction. And again, you should have this picture that coupling the S and the P wave orbitals should get you this rotating dipole. So to be able to do anything useful, once again, we need to quantify that we have long single molecule coherence times, but this time between rotational states rather than hyperfine states. Since we're atomic physicists, basically Ramsey and Rabi is all we know, right? This is another Ramsey experiment that we do. I won't explain it again, but we basically measure the Ramsey contrast of rotational superposition versus the precession time. And here we do perform a spin echo to rephase the sequence. And so here are our data. The pink data points were actually taken without the spin echo. So you see that we lose contrast within around 60 milliseconds. So that's long on the time scale of our interactions, but we weren't so satisfied with that. So we actually put in the rephasing spin echo and also saw the contrast decay, but this time in several hundred milliseconds. Now, we were curious to see what the source of the dephasing was. So we kicked around various ideas. Maybe there's a differential AC Stark shift, maybe time varying magnetic fields. We actually went to very low densities on purpose, 1% filling, to try to turn off the dipolar interaction in the system because we wanted to measure the single molecule coherence. But actually, we had to consider whether the dipolar interactions were at play. So we had a theory colleague, Alan Morningstar, who's in the back of the screen now. He actually computed from exact diagonalization the contrast of a 1% filled lattice gas molecules versus this Ramsey procession, and got this kind of black line. So to our delight and surprise, our blue data points are quite well captured by this black line, suggesting that even at 1%, like crazy dilute filling, our contrast was limited by many body effects rather than single body or like imperfections in the lab. So I will also acknowledge that this group at Harvard has performed Ramsey measurements and saw T2 times exceeding 100 milliseconds in a single molecule in an optical ether. So the takeaway here should be that we have very long coherence times on the time scale of our interaction, which is kilohertz level. And this is almost 2 orders of magnitude separation. So this makes molecules a very competitive platform for quantum simulation compared to similar systems with dipolar interactions, those being Rydberg atoms or magnetic atoms or NMRs. Yeah.
Sorry, but the coherence time is competitive, but the interaction is like 1,000 times weaker, right?
Right. I'm saying the ratio of the coherence to the interaction is competitive. Okay. But of course, we're much slower in absolute time compared to the first. So with that long T2 coherence time, let's go on to study various lattice spin models. So there's a natural mapping that takes the 2 rotational states as the pseudo-spin 1/2 system, and we're studying spin physics here. So there's a very generic Hamiltonian you can write down, this XYZ type model, which includes local interaction, Jij, with Ij being various lattice sites, and then you have couplings, which are the Pauli XX matrices, YY, and ZZ, or the Ij term. And in the biggest generality, those can come in with different weights. The Hamiltonian that's naturally implemented by our polar molecules is the so-called spin exchange Hamiltonian, which doesn't have the Ij term, and the X and Y terms come in with equal weights. And here, the interaction is nothing but the dipole-dipole interaction, which has the classic 1 minus 3 cosquare theta over R cubed term. And for us, the nearest neighbor V is very specific to every type of molecule. For sodium rubidium, it's 1 kilohertz for our optical lattice space. And I have to acknowledge that there was pioneering work done 10 years ago by the group of Juni, where they studied lattice-trapped potassium rubidium molecules. And there, when they did a Ramsey experiment, they found strange wiggles in the Ramsey contrast as a function of time. And they attributed these wiggles were exactly the nearest neighbor dipolar interaction. We extend this physics and we try to do a more comprehensive observation of thermalization in various lattice spin Hamiltonians. So like before, we do this Ramsey procedure where we plunge the upspin state into the equal superposition and process and perform the readout. The difference here is that we increase our filling fraction, 6 to 8% in this case, so that we can more clearly see the effects of the dipole-dipole couplings. We engineer the phase of the final readout pulse so that a molecule, which was initially in 1, will evolve into the down state in the absence of any dipolar interaction. So a single isolated molecule will go from up to down at the end of our Ramsey sequence if it doesn't talk to any other molecule. And for us, we cannot image the downspin molecules that appears as an empty lattice site. So let's look at the fraction of upspin as a function of Ramsey precession. As I explained before, at 0 time, there's no time for the interactions to build up, so all of the molecules are dark to our detection. But as time increases at early time, we see small clusters, pairs of molecules appearing. At later times, these clusters become larger and bigger in spatial extent until at late times, pretty much approaching half of the molecules are visible, and pretty much the entire sequence the entire array has been phased. So what's going on? Well, we are microscope experiments, so we're not limited to measuring just the bulk quantities like the magnetization. We can actually construct pairwise correlators, like this spin-up correlation function, and plot that in the bottom left as a function of time. So it's very interesting. At 2 milliseconds, you see that the correlation has developed strong correlations between nearest neighbor molecules. So this is versus Y and X separation. And that's exactly because the nearest neighbor dipolar interaction operates the fastest. So those nearest neighbor pairs get to face the first. And then it's the next nearest neighbor. And then next to next nearest neighbor, so on and so forth, until the entire ensemble is many-body entangled. Not only that, we can track the individual correlators as a function of time by post-selecting our data. You can look at the X nearest neighbor correlation, and it oscillates exactly at the frequency that we would predict from just calculating what the nearest neighbor dipolar interaction is. And this is the frequency that dominates this leftmost signal. We can do this for the diagonal neighbor. No surprise, it's slower by 1/r cubed, and so on and so forth for further and further neighbors. So there's a very pedagogical way to understand this. What's actually happening is that pairs are doing some entangling, disentangling dynamics. So for a very dilute gas, you can think of this as a gas of isolated molecules and pairs. So after one Ramsey sequence, the singles, as I explained, go into the dark state. You don't see it. But nearest neighbor pairs, you can solve exactly the XY spin exchange Hamiltonian for an initial product state of 2 upspin. And this is how it dynamically evolves as a function of time. You'll start with a product state down, down. You'll evolve into a Bell state of up minus down, down, and then a product state up, up, and so on and so forth. So we're basically creating Bell states that come in and out with some periodicity. Now, we did this in a very stochastic, haphazard way because we did not control the location of all of our molecules from shot to shot. However, our field has had 2 recent, I would call big achievements, landmark achievements, one by my colleague at Princeton, Lawrence Chuck, another from John Doyle's group at Harvard. So here, they can actually laser cool and image these calcium chloride molecules and trap them in tweezers. And because their imaging is kind of non-destructive, they can take a snapshot, bring 2 molecules close together, if there were molecules occupying that site, and when they're close together, operate the spin exchange Hamiltonian, deterministically try to entangle into a Bell state, separate the tweezers, and image. And they both measured Bell state fidelities of around 80%. So this 80% is, of course, not state of the art if you compare to the trapped ion platform, but this is the first time that it has been engineered with molecules. So that was very impressive. So also demonstrating the flexibility of the cold molecule platform, we can change its spatial anisotropy of the interaction. So because we couple the sphere to this donut wave function, you can imagine 2 scenarios. One, let's say you quantize that molecules that with a quantization axis perpendicular to your 3D plane. Then by inspection, you can see just from the shape of these wave functions, the interaction will be isotropic with regards to the X and Y direction. But if you tilt the quantization axis to be parallel to, let's say, the X dimension of your plane, then these donuts also become tilted. So along one axis, they'll be attractive, along another axis, they'll be repulsive. In the spin language, we can basically tune the ferromagnetism or the anti-ferromagnetism of our interaction. So let's go and do that. So the first case I showed you was an isotropic situation where the interaction was isotropic with regards to X and Y. And therefore, all of our correlations for all time, as shown here, are going to be isotropic. However, when we tilted the quantization axis to be parallel to the plane, you can see that our expected interaction becomes positive along one direction and weakly attractive along another. And then our correlations also develop a very pronounced anisotropy. And there's even an angle where the dipolar interaction is zeroed. And you can see that angle persist with no correlations for pretty much all times that we can measure. Not only can we engineer spatial anisotropy, but we can also engineer a spin anisotropic Hamiltonian. I'm running out of time, so I won't go into the details, but basically for experts, this is slow K engineering, pulsing on very rapid phase-controlled microwave pulses to engineer, for instance, this XYY Hamiltonian, where we've introduced this ZZIZ term. And we can, again, capture the magnetization and local correlation dynamics within this XYY model. And here is the magnetization and the local correlations with the theory curves from exact diagonalization. So approaching the end of my talk, I hope I've convinced you that molecules can be a very nice asset for the quantum sciences. They host very rich internal structure, which we can control. There are very long rotational nuclear spin coherence times, as I've demonstrated, and that is long compared to the interaction time scale of order milliseconds. And the interactions that we control are also very tunable. We can tune the spatial and the spin anisotropy and realize various different type of lattice spin Hamiltonians. And we developed this quantum gas microscopy for molecules, which enabled us to measure quantum correlations that are out of reach from traditional, let's say, condensed matter solid state type experiments. Looking into the future, I think this field is incredibly rich and has a lot of promise. So one interesting project that is within experimental reach is to create a fermionic gas of ultracold molecules. And if you confine this intensity and apply the right type of dipolar interaction, theorists have suggested that the ground state of this system is a topological P plus IP superfluid. And the excitement there is when you rotate this gas, you'll actually create little Majorana zero modes. So these quasi-particles that are their own annihilation operators. And of course, Majorana fermions have not yet been discovered in fundamental physics, but they can be created in these emergent systems, which is pretty neat. Looking further ahead, maybe a more diverse field of study might be to integrate molecules in the cavity QED regime, quantum electrodynamics. And there are applications in the cavity-aided direct laser cooling of molecules. You know, we always want to get to colder temperatures. You can use the cavity to steer chemical reactions by engineering the vacuum density of states. And this has been a long-standing goal in the chemistry community, but there are advantages for using ultracold molecules that are only populating one low vibrational state. And there you could perhaps model it with Hamiltonians in a cleaner way. And ultimately, there could be some application to study long-range spin physics, where you have the long or infinite range spin-spin interaction mediated by the cavity, but that's in competition with this local 1/r³ dipolar interaction. And we all know that in physics, when you have interactions that are competing on the same energy scales, very interesting physics can happen. And in a little bit further afield, another idea might be to use cold neutral atoms and trap them in twisted bilayer optical lattices. And these can be generated in a very arbitrary, software programmable way with modern laser and optics technology. And here, of course, the interest is to simulate the very rich physics that has been coming online with these twisted moire superlattices, for instance, bilayer systems and transition metal dicalcium. With that, I'm at the end of my talk. I would like to acknowledge that this was a big team effort. The first part of my talk was done at MIT under the supervision of Martin Zierlein with many grad students and postdocs and a theory collaborator, Tice. The later work was done in a group of Steve Bacher at Princeton, carried out by grad students Lysander, Jason, and Robin, and we also acknowledge our theory collaborators, David and Alan. Thanks for your attention.
Other questions, please?
Thanks for that amazing talk. When you showed us the correlation measurements was two-body, and it strikes me that with the Stirling factors you can have in the lattices, you can and should have higher order correlations. And so two parts of that question. One is, have you tried to see them? And two is, to what extent do they corrupt your two-body?
Absolutely. So there's something called the monogamy of entanglement, right? And for two particles to be completely entangled in an ideal Bell state, it better not be entangled with any third party or fourth party, etc. So indeed, as time evolves, we cannot think of nearest neighbors as being ideal Bell pairs because the entanglement has kind of been distributed across our array. However, our array is stochastically filled, as I mentioned before. We did think of measuring 3 and higher point correlators, not just pairwise correlators, but of course the attendant like signal to noise and the number of the data and shot that we would take would like scale in that way. So we decided maybe not to investigate that too carefully.
Yeah, and one follow-up question in a different direction. It's really tantalizing what you're able to do. and with just controlling those molecules, and it leads me to think that an EDM measurement with this platform would be incredible. Have you been, I mean, I know that's not your area, but I think the numbers would be impressive, or is there some background that just kind of makes it not so promising?
Right, I can only comment on what I've heard at colloquially and, talking to experts like Dave DeMille, Julie, John Doyle. They are leaders in the state-of-the-art electron EDM measurements. You have to pick the correct molecule species. You want to pick a molecule that has a very large internal electric field, so those would not be the bialkalies. So far, those state-of-the-art experiments have been using molecular beams to kind of interrogate molecules as they traverse like some spatial direction. The big interest is now laser cooling and trapping those molecules so they can have higher interrogation times, and with that push the EDM sensitivity down further. Will they get to the standard model EDM? Probably not, but hopefully they'll find something before then.
Thanks.
That's good. Quick, maybe technical question about this. So you showed us a lot of work with molecules you've done in optical lattices, and then there were a couple experiments recently pointed out using tweezer arrays.
Right.
Can you comment on what you think, the exciting next steps, or where you think that you'd like to go with that, or what do you do those two things?
Right, so my first proposal was neither. It was actually going back into a bulk two-dimensional trap, so you can develop like a harmonic confinement in 2 axes and strong confinement in either direction. It's just because the ground state of the system is the one that I'm interested in. Of course, the tweezer technology is fantastic. You can have software-defined geometries. The downside of tweezers compared to an interferometric lattice is that there's a lot of site-to-site disorder. So each tweezer is independently generated by like acoustic tone. So its intensity might be different from the nearest neighbor. So that introduces a disorder in the chemical potential. So whereas the interferometric lattice is very clean, but it restricts you to like a certain geometry. Yeah.
So I think this P plus IP idea is super cool. One thing that I struggled with when I tried to think about these kinds of challenges, one is to engineer the Hamiltonian, and the other is to cool into the many-body ground state.
Yeah.
Have you thought at all about how one might do that?
Absolutely. So here is where, so people in cold atoms have been trying to look at E-wave fluids for a long time, but that never really worked out because the energy scales are too low and the lifetime of an atomic gas near a P-wave mesh block resonance is too short. So the molecule allows you to engineer this longer range, attractive 1/R3 interaction. And so the length scale of that dipolar interaction, if that is comparable to the inner molecule spacing, then the critical temperature to see this phase becomes heavily raised. So Nigel Cooper and co-authors calculated like for lithium potassium a critical temperature of 10 nanokelvin as long as molecules were separated on order optical wavelengths.
But I thought the story often with these things is, you prepare some low entropy state, and then you turn on this interaction and you have to go through a phase transition. So even if your temperature is low enough, you close a bunch of gaps, and particularly for the topologically ordered ones, those gaps can be exponentially small in system size sometimes. So how does that story connect here?
Yeah, so we can discuss in further detail later, but like the general picture and the prescription is you take an already pretty cold molecular gas with no dipolar interactions. Maybe you do some further evaporative cooling to achieve the degeneracy factor, and then you adiabatically turn on a microwave dressed interaction. And I guess people think that connects to this P plus IP ground state of the system. And then you prove that you have the superfluid either by rotating the gas or doing some microwave spectroscopy on the gas. Measure the gap.
You mentioned the large number of internal states of these molecules as a benefit for the future, like in terms of additional things you could do. Are there concrete proposals that you have that leverage the internal degrees of freedom beyond just like the 2 or 3 states? electrodes.
Yeah, absolutely. It's kind of a waste to use molecules as two-level systems, right? There's like a big zero state. The one thing I didn't talk about was vibration, the vibrational substructure. Or my type of molecule is going to be like terahertz to 10 terahertz separated. You can hit that with like a 2-photon transition up to an electronically excited state. And the benefit of using a higher vibrational state is shelving. For instance, there are laser cooling proposals, kind of like with strontium, when you have a very stable, excited state that doesn't talk to the same transitions of your ground state, that can be leveraged for additional cooling. So yeah, I think it would be very cool to probe the vibrational structure.
Are there limits to the types of molecules you can work with, say those with ionic versus covalent bonds?
Absolutely. So there, the two methods I talked about, one which I do is basically restricted to combinations of species that can be laser cooled. So those are usually alkali. Some people are investigating alkaline earth with alkali, but so far no one has demonstrated ground state molecules in that nature. So bialkali is for the association type. For the direct laser cooling, this is going to get a bit technical, but you want to pick a molecule that has a very friendly structure such that you have a quasi two-level system. So most molecules, you try to have a two-level system, but when you excite the electronic degree of freedom, you decay back into a different vibrational state. So that means you don't have a diagonal Frank-Condon factor is what they call it. You have uncontrolled branching off into bad dark states. But there are certain classes of molecules. Think if you add a group 2 atom with a group 7 atom, well then it has one extra valence electron. It kind of looks like a hydrogen atom. This atom has a diagonal Frank-Condon factor such that it has a quasi two-level system where you can, with enough repumper lasers, cycle enough photons directly laser cool.
Thanks.
Couple more small things. One, if you try to do this physics in the bulk, won't the lifetimes be quite bad?
Yeah, actually, that's a great question. So there's a lot of chemistry that we don't want. You know, typically molecules coming in contact will undergo an uncontrolled inelastic collision. But this is actually where the microwave dressing actually helps. So at long range, that's where molecules can be thought of as point dipoles, this kind of rotating huge picture. That's where you have the long range attraction. But at short range, the molecules actually start to feel a dominant electric field from their neighbors, not from the microwave drive. So the intuitive picture at short range, they're always oriented head to head. And this is from the internal structure of the molecule. Unfortunately, there's no intuitive way to see this. But all you need to know is that short range is heavily repulsive. And this is not just theory. People like Emmanuel Bloch have been using the so-called microwave shielded evaporation, where if they go with the microwave in the correct regime, the correct parameters, they can actually turn off the inelastic collision and enhance the elastic collision. That's how they evaporate it and gain phase-based density.
One more in the back, and then John can go again. This may be related to Mark's question, but for the Hamiltonians that you can engineer in these systems, is it possible to engineer one where it's not just like where you have terms like SI dot SJ, but you also have SI dot SJ dot SK? You have 3 particle interaction or more.
A 3 or more particle interaction. Off the top of my head, I'm not aware of a direct prescription to achieve that. That's something I would be interested in learning about.
Any other questions for John again?
I mean, I can also ask that.
Yeah, but
Okay, then maybe, my last 4 questions. So looking at your rubidium mod insulator, you had a filling fraction of 80%, which seems quite
75.
low. What's the story there?
Yeah, that's you know, we didn't have a strong enough vertical confinement using the method of lattice that we implemented, and we tried a tighter spacing, like retroreflected at 1064 laser to get a 532 vertical lattice, like many people do, but then it was hard to load one layer at a time, or like populating many layers. So we decided not to focus on that.
I guess it doesn't matter, right? It's not.
Right, but like, yeah, you're right, in the future, we want to do the dual bond insulator approach, or that's one method that we think we can get higher fraction of the molecules.
Thanks.
Sure.
Well, this is a softball question, but I mean, like, these are tour de force hard experiments. And so I imagine that there's like a ton of stuff that goes wrong in the lab. And so-
Well, everything's smooth, what are you talking about?
What's the one thing that, you know, was like experiments that you described to us that, was just technically challenging on the lab side, like, was impeding like perfect data acquisition or.
The grad students are the real heroes of this project. It takes a lot of manpower to build up this experiment from scratch, just the lasers and the vacuum technology. I would say the two big challenges in my mind were just getting the dual species Bose-Einstein condensation. I kind of glossed over that, but that's not easy. Having two species is more than twice the difficulty of one species, because these two species talk to each other and you have to get everything right that works for both, not just one. So added to the fact that our cycle times are 30 to 40 seconds, it kind of is a slow data rate to improve on the experiment. You need patients to take images and then feedback in a very slow way. So I would say like optics, vacuum, electronics, it's all hard. It's all hard.
Well, thank you so much again, Zoe. So